Good afternoon, college algebra students. Well, I guess I don't know when you're watching this, but we can say afternoon. So today is the second of the videos that I'll be making for you for the week, and it involves using logs to solve equations. That's Wally, by the way. We're building our compost bin. In the previous lecture, we learned about all these logarithmic properties, but they're just kind of properties until we can put them to use. Right now, let's make them tools. So we're going to solve a bunch of equations. And without further ado, let's get into it. Whoop. And we'll go to full screen in black. So let's do a quick review of log properties. Right, one is the log of A plus the log of B. Do you guys remember this one? If I'm adding the two exponents, that's the same as multiplying the numbers, right? So that becomes the log of A times B, right? All right. Second one is very similar to that the log of A minus the log of B, well, that's the same as dividing. So that is the log of A over B. Right? And then finally, this was kind of an interesting one, that the log of A to the P power, right, if it's A to the P, well, that's kind of like A times A times A times A, which means we can add them all up, which means that this becomes P times the log of A. We can take this is one of the most useful ones. We can take this exponent and put it out front of the logarithm. All right, so that's that. So we can reference these. Now, if we're going to actually try to solve some equations, let's take a crack at a pretty basic one here. Let's say the log of x. And really all I'm going to do here is just solve a bunch of example problems, and hopefully this will help you solve some of your own. Let's say I have an example. The log of x plus the log of x plus 3 equals 1. Right, now if I don't put a base here, right, if there's no base shown, what does that mean? That means that I'm implying that the base is 10. So it's a log base 10, log base 10. All right, and that's important to remember. Well, what I want to get, my goal in general is just have one logarithm, or worst case scenario, one log on both sides. So can I combine these things into one? Sure I can, using this property up here, this addition multiplication property. I can rewrite this as the log of x times x plus 3 equals 1. Or I can do a little housekeeping inside and say it's the log of x squared plus 3x equals 1. All right, now we've got some options. What exponent do I need above a 10 to get this? Well, that exponent is a 1. I know what the exponent is, so I can rewrite an exponential. I'm going to rewrite this expression in exponential form, which means that 10 to the first power equals x squared plus 3x, right? Where did that 10 come from? That was the base here that we implied in green. So 10 to the x equals x squared plus 3x. Well, this looks a little familiar. I can rewrite this like this. I'll subtract the 10 from both sides and say that x squared plus 3x minus 10 equals 0. All right. Well, next page. Now, this is just a quadratic. I wonder if I can factor this thing. In fact, I'll factor it down here. So so I know I need an x times an x. And let's see, multiplies to negative 10 adds to positive 3, so I'm going to say plus 5 and minus 2. Does that work? X squared plus 5x minus 2x. Yep, that's plus 3x minus 10. Good. So I can go from there and say that x plus 5 equals 0, or x minus 2 equals 0, which means that x equals negative 5, or x equals 2. Now, we have to use some caution here. I'm going to write this in red. Caution. Check answers. Alright, so let's check these here. I said the log of x plus the log of x plus 3 equals 1. So, let's check the first one. The log of negative 5 plus the log of negative 5 plus 3 is negative 2 equals 1. Wait a minute. The log of a negative number? Right? Well, my log graph looks like this. Let's do a quick little sidebar here. So I know my log graph looks something like this, right? There are no negative numbers, right? There's no negative. There's no negatives in here, so this can't be. And for that matter, this can't be, right? So this doesn't work. Negative 5 doesn't work. All right, so we better check our 2. Let's check the 2 answers since we found that that 1 didn't work. First of all, let's erase this. Eraser. Sometimes I get excited and I make extra lines. So let's say the log of 2 plus the log of, let's see, in my original equation 2 plus 3, so that would be 5 equals 1. So that's the log of 10. 2 times 5 equals 1. The log of 10 equals 1. What exponent do I need above a 10 to get a 10? What exponent do I need above a 10 to get 10? That equals 1. That checks out, so this is my good answer. Keep this one, and this is what we call extraneous solution. Right. Now, why does it happen that way? Because we converted a log formula to a quadratic formula, right? A log equation to a quadratic equation. This quadratic will give us some results, but some of the results may not work back in the original. That's why you always check your answers. All right? Good. So let's move on to the next page, and let's try another one. Back in black, another example. Whoop. Example. All right. The next one we'll try is the log of x plus 12. Minus the log of x equals the log of x plus 9. I don't know why I'm accidentally hitting my eraser all the time here. The log of x plus 9. All right, well, again, my goal is to have one log on each side, so I'm going to combine these two. I'm going to say that x plus 12 over x, right? So this becomes the log of x plus 12 over x equals the log of x plus 9. Now, I've got two options. I could rewrite each of these in exponential notation, except that this isn't really a log of something that equals a number. This is the log of something that equals some other log of something. So let's think carefully about this. I'm going to rewrite this. Again, the base here is 10, because if there's no base, we assume it's 10. Equals the log base 10 of x plus 9. What does this mean? What exponent do I need above a 10 to get x plus 12 over x? No idea. Well, it's the same as what exponent do I need above a 10 to get x plus 9? Well, if the exponent I need above a 10 to get this is the same as the exponent I need above a 10 to get this, that must mean that x plus 12 over x has got to be the same as x plus 9. It's got to be, right? If the logs are the same, then the quantities have got to be the same. Okay, well now how do I solve this one? Multiply through by x, and just in case, I'll write this out. Multiply both sides here by x, and that gives us x plus 12 equals x squared plus 9x. Yet another quadratic equation here. I'm going to subtract an x and subtract a 12 from both sides. So x squared, let's see, plus 8x. Subtract an x from here, it gives me plus 8x. The x squared remains, and then minus a 12 equals, let's see, 0. Okay. Well, let's see if this one factors. I need two things multiplied together to give me this. X times x. Well, I've got to get negative 12, so one of them's got to be positive, one's got to be negative. 1 and 12. No, that doesn't work. 2 and 6. Ooh, might be, no, but one's got to be positive, one's got to be negative. 2 and 6 will not work. 3 and 4. Negative 3, positive 4. No, that doesn't work. 6 and 2. Huh. Shoot. So this one doesn't factor. So what do we have to do? Oh, well, fortunately we developed this tool that says x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So what does that mean? Negative b, so it's negative 8 plus or minus the square root of b squared, 64, minus 4 times a, which is 1, times c, all over 2 times 1. So that equals, I better put an equal sign there, keep my good bookkeeping. So let's just keep the negative 8 there, and it'll be plus or minus. So 64 minus 48, I happen to know that that's 64 minus 48 is, wait, where I lost my place here. Plus or minus, is that 16? I didn't think this one works out. All over 2. So that equals, oh, square root of 16, that's why it is. Ah, shoot. Hold on, I gotta pause this for a second. I made a mistake somewhere. This shouldn't have worked out this well. Okay, I found my mistake. So, negative 12, right? I missed a negative sign. 4ac, so this is actually down here. This should have been negative signs matter. 4 times 1 times negative 12, which is, that changes this over here. So this is 64 plus 48, which by my math gives me 112. So this becomes the square root of 112. Now these get kind of tricky. I know I can get a 4 out of here, right? So that'll be 28. So, but I can get another 4 out of there, so that means 16 must go into this. So it's going to be negative 8 plus or minus the square root of, this is 16 times 7, I think, works out. Yeah. All divided by 2. Right? So that equals negative 8 plus or minus the square root of 16 times the square root of 7 all over 2. Now I know this is trivial for some of you, but I know some still struggle with radicals, so I'm going to go through the whole thing. Or I might mix a negative sign. So this is 4 root 7 all over 2, which means this simplifies down to negative 4 plus or minus 2 root 7. Okay? Now, in Alex, this would be negative 4 plus 2 root 7 and, or comma, negative 4 minus 2 root 7, right? 2 solutions for that. And so this would be our final answer for that. Now notice that, let's see, well, let's review the problem here. I combined the 2 logs, and then I set the 2 logs equal to each other. All right, my logarithm part of it is done. All this work I did then was just old algebra, right? Quadratic equations. These quadratic stuff is very, very important. It comes up all the time. But the key thing is that if I knew the logs are equal, that means the arguments of the logs must be equal. All right. Now, the much more powerful application of this log stuff is cool. Let's call this a cooler example. Is if I have some equation and I said, say, 4 to the 3x minus 1 equals 8. Wow. So what is this? In this case, my variable is stuck up here in my exponent. My x is up in an exponent. I've never had to deal with this before. Boy, I don't know. What am I going to do? Well, the first thing I can do is just say, well, let's get rid of this 1. Let's add that to the other side. So at least I can say, we're going to just add a 1 to both sides, plus 1 plus 1. And so now we're at 4 to the 3x equals 9. So I don't know the exponent. This becomes all of a sudden really tricky. So I'm going to take the log of both sides, right? Because the log allows me to get up at this exponent. Why does the log allow me to get up at the exponent? Partly because of this log property back here. Right? This allows me to get at it. So let's fast forward here. So I'm going to say that the log, I'm going to apply this function to both sides of 4 to the 3x equals the log of 9. Now, it's very, very important. This is not multiplying both sides by log. Someone's going to say that. I multiplied both sides by log. I am not multiplying. This is a function. I'm putting both of these things, both of these quantities, into a box that I call my logarithm box. Now, what does this allow me to do? This allows me to say that this exponent can come out front. So I'm going to write 2 options. Option 1, or option A. I'm going to go this way. And option B, no, that sucks. Undo that. Option B is over here, and that's going to go this way. All right, option A. I'm going to take the log of both sides, and I'm going to just say that 3x times the log of 4 equals the log of 9. Remember, this is base 10. Okay, so I'm going to actually put a base in there. Just because if we don't say anything else, it's log base 10. Well, now this is multiplied. 3 is multiplied by the x, which is multiplied by the log of 4. So I can divide both sides by the log of 4. Do that in blue. So I'm going to divide by the log of 4, divide by the log of 4. So now I've got 3x equals the log of 9 over the log of 4. And then I can divide by 3, right, because I want to get my the 3 by itself, or the x by itself. So divide both sides by 3, divide this whole thing by 3, and this is x equals the log of 9 divided by 3 times the log of 4. All right, fine. Another way to write that is x equals 1/3 times log of 9 divided by the log of 4. Now, what about option B? I'm going to do the same thing. I'm going to bring the exponent out front. I'm going to say that 3x times the log of 4 equals the log of 9. Now, still very important. I'm not multiplying by the log, right? This is a function. I'm putting my 4 in a box and I'm putting my 9 in my box. But here I'm going to be clever. I don't have to take the log base 10 of both sides. What if I took the log base 4 of both sides? I can take whatever base I want, right? And just stick it, as long as I stick both sides into the same box, in this case the log base 4, I'm good. What does this mean? The log base 4 of 4. What exponent do I need above a 4 to get a 4? Wait, what exponent do I need above a 4 to get 4? Well, that's 1, right? So this is really 3x times 1 equals log base 4 of 9. Then I'm going to divide both sides by 3 here, because this is really just 3x equals log base 4 of 9. Well, x equals 1/3 log base 4 of 9. Now, some of you might be saying, what is going on here? In fact, let's make a big, fat, red question mark. What? How could I have 2 different answers? 2 different answers? So the question becomes, is 1/3 of the log base 9 over the log base 4 the same as, right? Is this the same as, equal sign with a question mark, 1/3 log base 4 of 9? Is that the same? Well, 1/3 and 1/3, right? That's easy enough, so I know that works out, right? We'll use the red pen of cancellation. Those are okay. So now we're left with the log base 9, log of 9 over the log of 4 equals log base 4 of 9? Sure it is, right? This is the change of base. If I want to change the base, like say I want to go log base 4 of 9 equals log base 10, what do? We just change it, right? You want to change the base? Change the base. Make it a 9. But then we have to divide by the log of the old base, right? So these are the same. They're just different bases. They look different. This is slightly more clever. Right? Why is that? Because I was able to do it in a lot fewer steps because I chose my base carefully. Right? Doesn't matter what base you pick; it all works out the same. Right? But in this case, I saved myself a little effort by picking a clever base. All right. So let's move on. Let's do another example here. And let's do, oh yeah, we haven't done with natural logs yet. So let's say a natural log example. My handwriting's degrading here. So remember, the natural log of x is the log base e of x, right? And e is approximately equal to 2.718 ... It goes on forever, right? It's a very special number, which we talked about briefly. Okay. Well, now I've got an equation that says the natural log of 5 to the x plus 1 equals the natural log of 6 to the 2x. All right, so whatever are we going to do here? Well, when I first look at this, I see here's an exponent stuck up in the variable. The variable is stuck up in the exponent. Same here, variable stuck up in the exponent. So I'm going to use this property where I can move the exponent up front. So I'm going to say this is x plus 1 times the natural log of 5 equals 2x times the natural log of 6. Okay. So now I'm going to, boy, I've got x's all over the place. Let's distribute this. So this is x times the natural log of 5 plus 1 times the natural log of 5, which is just natural log of 5, equals 2x natural log of 6. What did I do here? This is just distribute. Okay. Now I've got an x here and I've got an x here. They're both mixed up in these ugly looking things. I'm going to collect all the things over here that have x's. So I'm going to say that x times the natural log of 5 minus 2x times the natural log of 6 equals, the only thing that doesn't is this. I'm going to subtract to the other side, negative natural log of 5. So I'm going to collect x's on the left. That's what I'm going to call that. Collect x on left. Right. So I subtracted this over, subtracted that over, so all my x terms are now on one side. And then here's what really confuses people. Now I'm going to factor an x out of both of these. X times the natural log of 5 minus 2 natural log 6 equals negative natural log of 5. Alright, what did I do? I factored these, both have an x. I got the x out of there. Why do I do that? Because that allows me to get x by itself. I'm going to divide by ln of 5 minus 2 ln of 6, divide by natural log of 5 minus 2 ln of 6. So what do I have now? All I have left here is just my x equals negative ln of 5 divided by ln of 5 minus 2 ln of 6. All right, so we have successfully solved for x. All right. Now I can take this a little further. All right, take this just a little bit further. Just a bit further. I'm going to say that x equals negative natural log of 5 divided by, I can say natural log of 5 minus whoa, how did I get that? Well, because I had 2 natural log of 6, I can put the exponent up top, right? And that rule works both ways. So 6 squared is 36. And this equals, I'm going to use another property, negative natural log of 5 divided by, I'm subtracting exponents here, that's the same as dividing the numbers. So this becomes the natural log of 5 over 36. Okay? Now, I call this a good enough answer, right? X alone, here we have some logarithms. We could punch this into our calculator and find that X equals, well, what does X equal? I'll punch it in, punch, 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 and I get approximately 0. I better change that. I'm going to label this. This is very important. This is exact answer. Right? Did I round off there at all? Nope, this is exact. I didn't round anything. I didn't drop any decimal places. So down here I can say that X is approximately equal to, right? It's approximately equal to 0.8153 dot, 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 right? It's going to go on forever. So this is not the exact answer anymore. This is, in fact, I'm going to do this in red because red is generally bad. Approximate answer. Right? If this were years, well, maybe 0.8153 is enough, right? It gets me down to the day or the hour. Right? If this were dollars, maybe, just stop it at 82 cents. It depends. Once we start approximating, we have to be very careful. Usually I will ask for the exact answer. On occasion, you have to punch these numbers into your calculator to get an approximate answer. Okay? Big difference. So what else? I think we're pretty good. Key thing is to understand these log properties that we reviewed at the very beginning. If we remember these 3 log properties, these important ones, then you can use those as tools to solve logarithmic equations. In the real world, and especially in the fields of science and engineering, finance, biology, ecology, populations growing and decaying and stuff like that. Logs and natural logs show up all the time. So especially natural logs. For those going into biology, ecology kind of stuff, natural logs show up a lot. Okay, that's it. I hope that helped. I will see you guys next week.